morning. This talk is a joint work with okay. Hello. So this talk is a joint work with Guy Golan-Guetta from Yao Research and my advisor, Professor Edith Kedar. So this talk is about multithreading. Multithreading is everywhere now, and we need to make software multithreading, good multithreading. So today we have to choose between two approaches. We have that are widely used, and on the other side we have transactional software memory that are less used. I will first and then I will introduce to you our new concept that combines these two approaches. All this, and I will show you its evaluation. I think so. Sorry. Okay, so you hear me? Yeah. Structures that are very popular. Almost every application uses them. We all know them. We all like them. We have queues. But are they thread safe? What happened to many threads access them concurrently? What happens to the operations? So there is so-called threads, many work data structure libraries. You have here some in the literature. There's libraries in real life. You can find implementation in Java, many other languages, and you have an application. It picks some concurrent data structure, and the implementation of the data structures guarantee that threads that access concurrently the data structure will be performed atomically. And it's important to note that the implementation of data structure is custom to the specific semantic and structure of the data structure. The operations are very good. The question is it good enough? And how we use it. So here we have the classic map that stores keys and balances, and we want to increase it locally and set it back. If two threads running this code concurrently, then atomic, we can lose one. If two threads will read the balance, then one of the stores back can be lost. So we see that a single atomic operation are not enough in multi-threading software. So this observation is actually not new, and this was the motivation for software transactional memory. The idea of software transactional memory is to take a block of code, to wrap it up between begin transaction and end transaction, and the implementation of the software transactional memory guarantees that each such transaction will be performed atomically. And in case it detects a conflict between two transactions, then one of the transactions will be aborted and we'll have to retry later. And you can see in the figure here that the STM, the implementation of the STM, does not know what runs on top of it. So in our example, we have the map and the queue that running on top of the STM. So the STM implementation cannot take advantage of the specific semantic and structure of the data structure. The STM is very general, and therefore its performance is much worse than the concurrent data structure libraries that we saw before. Okay, so this is the summary of what we have today. Which do use the semantic and structure of the data structures, and therefore they have very good performance in real life. But they are not general and they are not composable. And by generality, I mean that they support only data structure operation. They cannot support arbitrary memory access. And by composability, I mean that, as in the example before, we cannot take several data structure operation and perform them atomically together. Software transactional memory, on the other hand, is general and composable, but its performance is much worse. Okay, so this was the motivation, and now I will introduce you our new concept, which is transactional data structure libraries, TDSL in short. It combines the two approaches together. So we start with data structure that we know work and know are fast, and we wrap them up inside the transactional library. We does not run the data structures on top of the library as in the standard way. Instead, we implement everything together. We add to the library support to begin transaction, end transaction, and we support transaction of multiple data structure operation. So we get the programmability of a software transactional memory. But because our implementation is custom tailored and we know exactly what data structure we support and we implement everything together, we can take advantage of the specific semantic and structure, and our performance is good, is almost as good as concurrent data structure libraries. Okay, and in addition to this, we also wanted to support legacy code. And for legacy code, we need to support fast and abort-free single operation, which we call the Singletons. This is the same operation like in the concurrent data structure libraries, without the begin transaction, end transaction, just get in queue. Okay. So you were probably asking yourself, where is the catch? Because I told you that transactional libraries are not fast, and then I said that we implement a transaction library that is fast. And the thing is, how we do it is because we give up generality. We restrict our transaction to span only over data structure operation. We does not support arbitrary memory access like the standard STM, but this allows us to gain performance. Okay, so our concept has several benefits. The first one is about it. We have the power of transaction, and we also support fast abort-free singletons. The second one is that because we implement everything together, we use the semantic optimization in order to reduce the overhead and the abort rate. We still can use some known technique from software transactional memory, but now we can do. Here is an example of how we can reduce the abort rate. So suppose we are running concurrently, one insert 23. So it begins by traversing the list, and everything it reads, it's stored in some read set that we'll have to validate later. And then, before the commit, another transaction comes and tries to insert 4. This transaction modifies one of the nodes. So the first transaction has a read-write conflict, right? Because it wrote a version, and then this version changed, so it has to abort in the standard STMs. But there is no real semantic conflict here. So there is no problem here to perform these two operations concurrently, because semantically they are commutative. Okay, so our third benefit is what we call mix and match. And some of the data structure are inherently very good with concurrency. For example, maps and queues have commutative operation, as we saw in the example. So in this case, we would like to use optimistic concurrency control. On the other hand, there is data structure like queues, for example, that are very good, are better with pessimistic concurrency control, because point of contention on the head and then the tail. So concurrent operation will like have conflicts. So in our approach, we can, because we implement everything together, we can implement some of the data structure optimistically, others pessimistically, while in standard STMs picks only one and implement everything together, and therefore one of the data structure will suffer. Okay. So this is the idea, and now I will show you an example of it. We implemented a library with Skiplist. I will show you the Skiplist now. This is the roadmap of the implementation. We started with a sequential skip list, not efficient at all, and we added to it a STM mechanism. Okay. Then we added two optimization to it. The first one in the first structure to reduce the abort rates of the STM. The non-transactional index, and I will talk about it later in a few slides, operation faster and reduce the abort rates even more. So, first step, we take a linked list, simple linked list, and we add to it a TLS. To do it, we need to add a version to each clock that each transaction read at the beginning. The transaction maintain read set and write set, everything it in the read set and validate later at the commit phase. Written to the write set and the first phase. And during the commit phase, lock the write set, validate the read set, in clock and update. This is the standard way memory would work. Okay, so 10, we start by reading the global version clock, then we traverse the list until we find to actually insert the 10. Everything we read during this traverse, and this 10, 17, we put in the read set, and the actual node that we want to update to the write set. And it's also the list, we need to validate each of the is not bigger of the version that we read in the beginning. Sure that we are still in the main list and we are not on. So we need to validate. Okay. We use the semantics, and as we saw in the example, in order to satisfy the semantics of the skip is to validate in the commit phase only the predecessor. Conflict in earlier nodes. So the read we only put the predecessor there. Reduce the overhead because now the read sets are small, and this is also reduce the abort rate because we does not abort if we see read-write conflicts as in the example. But we still have to traverse the list, and we still will with a newer version than ours. The third step is a non-transactional index. Insert node number 10, and you somehow guess node number 9. So you could just steal node, and that's all. You will not have and your operation will be very fast and during the traversals. This is what the skip list will give you, right? The upper levels of the skip list. It is important that what we do is non-transactional, because if you have lists, so you have to maintain big read sets because you traverse the layers, and you also can conflicts on this skip list will also lead to aborts, and we want to avoid it. So we use an external that supports add node, remove node, and get smaller is simply I give the told me another node with a key smaller that I give it. Implemented it as a skip list. There was no problem to implement it as a skip outside the transaction. Example, now when we want to insert 10, we first go to the index with a key that is smaller than 10, and number 5, we go to node number 5, to node with key 5, and we continue. So, and we update this non-transactional index when we successfully commit a transaction. And because we update this transaction, so conflicts on this index cannot lead, and we also, as I said, don't need to maintain huge. Okay, so this is good, but some issues because we updated outside the transaction. There could be some races because, for example, can return me a node with a key that is not the predecessor. It can return me a key that is smaller than the predecessor. Like in the example, you see, I wanted to answer that's not familiar with node number 9 because it just now was added and the index. So it returned me the node number 5. Problem, it may a little bit impact performance, but a real problem. Another thing that can happen that this index can return me a delete. This is a little bit more subtle, and I will not read in the paper. Okay. Skip list, and now I want to speak a little bit of how we multiple data structures. I want a transaction to span over a skip list and the. So this is actually pretty very shared global version clock among all the objects. Version clock in the beginning, like before. Then the operation. All we need to do is change a little bit the commit phase. Now we sets of all the objects sequentially. Then we validate all the increment the global version clock, and we update all the objects and release all the locks. Okay. So I also want to speak a little bit singleton fast. As I said, fast single operation for legacy code, and so what we did, we not increment the global version clock. The global version clock is the point of contention. We wanted to avoid it, but we still have the transaction to somehow be able to abort if necessary, if the singleton changes. Know about it, in order to. So there is some subtle, not get into the details, but you can. Okay. To talk a little bit about library composition. Our library supports transaction, and if it's still important to you to get the general and arbitrary memory access, what you can compose our library with a standard. To do is to support a search API. Actually, very natural to support in TL2 like other two-phase locking approaches. The details of this API, but you can see it in the paper. But, when you have a transaction that is only span over data structures, it will be very fast. If necessary, have a general transaction. You can still support it. Okay. Okay, now I will talk a little bit about we implemented our library in C++ and we compare it to other works with. And in this graph, we wanted to compare our single operation with the. Now it's important to see this data structure does not support transactions. This is the data one atomic operation, and this And we can see this that our skip list the others. And what another our skip list, the black one, is as good as the baseline. Is the skip list that we use in order to implement our index. Better than the index, but it shows that we have no much overhead. Okay, we also compare our transactions to a sequential skip list running on top of and also with some friendly library that uses TL2. Here we see workload and an update only workload. It's also a throughput graph. So, and the read-only workload suggests that we reduce with our optimization, and therefore we're better here. The update-only workload suggests that we have much less aborts than the sequential over TL2. Yeah. We also wanted to test our library with a real, which is some network application that use multiple index and maps, and we compare it to intruder over TL2. We TL2 because it does not support intruder. It can list and does not have iterators. And here we see also the abort rates graph. TL2 has a lot of aborts. And this is because we think this is because we implement the queue in a pessimistic way. So we think that the aborts almost to minimum. Okay. A few words about related work. The semantics, inside the transaction, there are several papers, and there are more papers in the literature. Discuss this in details in the paper, and you can read or you can ask. And okay, so we married the idea of concurrent data structure library, transactional memory, and we introduced a new concept which we call TDSL, transactional data structure libraries. We implemented an example library, and I show you its evaluation. And we really hope that that others will follow us and build more such libraries in the future. Thank you. The optimization specific to the skip list, but you can do each data structure you can optimize according and structure. For example, the queuing, because like I said, we use an optimistic concurrency control for the queue. Are you asking about the generality of the libraries or the generality of both? So transactional index, in the same way that we did the skip list, we can do it for balance trees. We can generate it to the balance trees. We can have the leaf layer transactional and all the non-transactional. And for the library compositions, as I said, our structure operation, but you can take a standard STM implementation and you have to support transaction in our library, begin transaction. You can do it together.
Okay, so another question I had was about the structure that you presented, the optimistic tree, I think, in the read-only, it has such bad performance in the read-only case.
Yeah.
For the singletons. This one, so the optimistic, is that really optimistic, or what does it do?
This was the implementation in Synchrobench, so we just have, and this is the result. So I see what they are doing. What?
Okay, thank you.
I mean, your definition of composition is focusing on of atomicity.
Yeah, atomicity and opacity also.
Yeah, okay. So what about composition? Third-party software that may or may not have shared objects with your data structures. So what kind of assumptions do you make on like separation of objects or heap or something? Do you require, for example, when you compose with another concurrent data structure that doesn't use any of your API?
When I compose between different data sets, implement everything inside our library, all our library. I only talked about how data structured inside our library, and if we want to compose it, we need that this library will support it.
So sorry, let me rephrase the question. So assuming if you are composing with another library that doesn't structures or
okay, yeah,
just completely different memory space,
yeah,
is there a way to actually also integrate it with this framework, or you actually also have to instrument it with your API? It's not very clear because this is the kind of composition you would like to have as well.
You don't need to change anything except that you want it to support the source. TL2, it's very natural to support this API. You just want to begin divide the commit phase to locking, validation, and updating. The TL2 can be in a separate memory, our library in a separate memory. Yeah. We can just begin transaction here, and do all the phase of like validate this, validate this.